Well, good afternoon. It's 12 o'clock, so let's get started. My name is Pat Whitcomb. I'll be presenting the webinar. Sherry Kramer will be monitoring the webinar and be available to answer your questions. So if during the webinar you have a question, then type it in to the Ask Question box and Sherry will answer that for you. All of you are muted, so I won't be able to hear you, so you'll have to communicate using the chat box with Sherry. Okay, I'm going to talk about KCV models. These are models that streamline the process of doing combined mixture process designs. I'm really excited about these models. They've been a huge benefit since they came out. So KCV models are models that are used for combining mixtures and process. And the KCV comes from the developer, Scott Kowalski. He developed these as part of his PhD thesis, and his advisor, Geoff Vining, and they worked in concert with John Cornell, who was the mixture guru for many years. Okay, and this is a reference to the paper I'm taking my talk from and that we've used to implement KCV models in Design Expert. There's also explanations of these models in the book that Mark Martin and I have written on using mixture design, Formulation Simplified. And I'm going to first talk about KCV models, then go through a very simple example, and then show an actual application of the KCV models in my talk today. So the reason to combine mixture components and process factors into a single DOE is so that we can model the dependence of one on the other. If the effects of the mixture are completely independent of the processing conditions, then we could just do a design and optimize the mixture and do another design and optimize the process. But quite often, the best processing conditions depend on what the mixture is and vice versa. Okay, so we've got the mixture equation. So I'm going to, throughout this talk, just use a quadratic equation. You could use a higher order equation. All the principles would apply. And you've got a process equation. Okay, so for mixture, we've got the Chaffee form, where we've got the coefficients on the individual components. The components are proportions that add up to 1. The intercept gets embedded in the linear coefficients, so there's no intercept. And the xi, xj term are called mixture quadratic terms, and those represent curvature, unlike the zk, zl, the interaction terms, which represent a twist in a plane, but can't model curvature. So remember, in a mixture, what looks like an interaction is really a quadratic term. So those are called mixture quadratic terms. Then we've got the second order equation for the process with an intercept, the linear terms, the interaction, and the squared terms. That's an ordinary polynomial. Now, when you cross those, when I multiply the mixture times the intercept's just a constant, so I get what looks like the quadratic mixture back. Then I multiply the mixture times the linear terms for the process, and so what you get then is the correction. Think of this as the average blending properties. And then I get a correction to those average blending properties in the linear part for the level of the process factor, and a correction to the mixture curvature for the level of the process factors. That's what these are. These are corrections to those average blending properties. Then what we do is we cross the mixture with the interaction term. And again, now I'm getting the correction to the linear blending for the interaction between the process factors and a correction to the quadratic blending for the interaction between the process factors. Then I multiply it times the squared terms, and I'm going to get a correction to the linear blending for the quadratic correction for the process factors, and then a quadratic correction to the curvature in the mixture part for the process factors. Okay, so everything is crossed and connected. Now, another way to do a model instead of crossing them and multiplying them together is I could do an additive model. And so the advantage of an additive model is it has fewer coefficients. Now remember, the minimum number of runs, the absolute minimum number of runs to fit an equation requires one run for every coefficient. So if you have fewer coefficients, you can get by with fewer runs and therefore less work. So that's intriguing to have fewer runs. However, the ability to model the dependence on the mixture and the process factors is completely lost when you just do an additive model. So an additive model is we just add them together. So we just take the mixture part and we add to that the process part. Remember, this intercept is already present, embedded in the linear part of the mixture, so that just makes a correction to that term. It's not a new term. So you just add these together. Now, a cross model completely links the mixture components and the process factors. Everything's crossed. The problem is that gives us good ability to model the dependence of the mixture on the process and vice versa. The problem is we generate a lot of coefficients. That means we have to do a lot of runs in our experiments to estimate those coefficients. Now, the additive model has the advantage that it's a smaller model. It requires fewer runs. However, there's no linkage between mixture and the process that doesn't contain any crossed product terms. So we might as well just do a separate design on the mixture components and the process factors. Okay, so there can't be any dependence of one of those on the other. So as a compromise, it was that was proposed by Scott as part of his thesis was to have some of both. Okay, so Scott and Geoff worked on this and then presented it and collaborated with John Cornell to finish it up. And in their approach, the linear models were crossed. So you take the linear part of whatever model you're doing and cross it, and then the higher order terms are added. So again, if we do the quadratic, here's the cross linear model. So I've got the linear from the mixture multiplied by the linear from the process, and that's going to give me the linear terms. Remember, this intercept's already embedded in the linear terms, and then the linear term for the process times the linear term for the mixture. So that's here. So those are crossed. Then what we're going to do is we're going to take the second order terms from the mixture and we just add those in. They don't get crossed. And the second order terms, so the two factor interactions and the squared terms from the process, and you add those in. So in this KCV model, the red terms are coming from crossing the linear terms, and the blue terms are coming from adding in the second order terms. Okay, if we had 3 mixture components and 2 process factors, then what we're going to do is we're going to cross the linear part with the linear part from the process. So that gives us this times the intercept gives us what looks like the mixture. So those are the average blending properties. This times the coefficient for Z4 gives us the correction to the average blending properties for the level of the first process factors. This times Z5 gives us the correction to the average blending properties for the level of the second process factor. Then we add in the higher order terms for the mixture, and we add in the higher order terms for the process. and that gives us the KCV model. Cross the linear terms, add in all higher order terms. Okay, so if you compare this with doing the straight additive model for 3 mixture components and 2 process factors, that would have 11 terms. This has more terms, it has 15, but not that many more. Compared to the crossed model, if I did the crossed model, it's going to have 36 terms. So you can see that the KCV model in terms of coefficients has the number of coefficients is much closer to the additive model than it is to the cross model. So it gives us something that's going to be practical to run, but also gives us connection between the mixture and the process factors. Okay, looking at this for just some different combinations, you can look at the KCV model compared to the additive model. It's always bigger, but not by a huge amount. If you compare it to the fully crossed model, now when you have many mixture and process factors, you get higher order terms, quartic terms and 5th order terms and 6th order terms and going on up. And so what we often do if we're going to cross the model is we drop the terms above a certain order. So if we did a quadratic by quadratic, but we only kept up to 3rd order terms, that would be what we'd typically fit with the cross model. And you can see that really reduces as the number of terms go up, really reduces the number of experiments, but it's still many more experiments than what you'd have doing the KCV model. So the KCV model, in terms of number of coefficients, is always much closer to additive than it is to crossed, even if we try to reduce the crossed model. Okay, now this is something I noticed when they published their paper, that these KCV models are actually just a remapping of ratio models. Okay, for those of you that aren't familiar with ratio models, back before there were a lot of computer programs for doing mixtures, we still had to account that in a mixture, what was important were the proportions of the ingredients, and that the ingredients add up to a constant, and that reduces the dimensionality by 1. So when you have 3 components, you have a 2-dimensional problem. That's why you see it on triangular graph paper. Once you specify 2 of the 3 ingredients, the 3rd one gets set by the equality constraint. And so we'd use ratios, and we'd always use 1 less ratio than the number of components. Okay, then now we're using ratios, so we're accounting for the mixture effects as proportions. 1 less ratio than the number of components. That's accounting for the fact that you can't change the last component independent of the others. So you can only change if there's Q components, Q minus 1, the last one gets set by the equality constraint. So we'd use ratios. And if you look at what we do is you just put the ratios then into an ordinary polynomial. Okay, so you've got the linear terms, the interaction terms, and the squared terms. Okay, for all of those things, you're just using ratios. If you look at the KCV models, they always have exactly the same number of coefficients as using ratio models, and they have the exact linkages. If you look at where there's X's and Z's, and you look over here where there's R's and Z's, they're always linear by linear corrections. Okay? And so this made me feel a lot better about using the KCV models because they're essentially equivalent to ratio models, but they have a big advantage. With a ratio model, using ratios limits how well you can fill the design space you're studying because you can only run runs where the ratios cross each other. Treating the components as components, you can completely fill the design. Okay, so now we've got models that are equivalent, but using the KCV model means I can get a better design because I can better fill the space I'm looking at. Okay, now this made me feel really good because I'd used ratio models in my own work for years before we had computer software to handle mixture components. and had lots of success. There are a lot of papers published, and lots of my contemporaries used ratio models because it's the best we could do with the tools we had. Okay, so now we have a model that's equivalent, but it's going to fill the space better. So that's even a step forward. Okay, so let's look at a simple example, made up example, where we're going to build a 3-mixture, 2-process variable design, and we're going to use a KCV model. Okay, I've taken some of this material from our training, so it's spelled out as do this step, because I just stole it from the training, and normally the participants would be doing these exercises. You're just going to be looking at the exercises and imagine yourself doing them. Okay, so here we're going to pick an optimal design. We're going to have 3 mixture components and 2 process factors or numeric factors. Here's our mixture components. We're just going to call them A, B, and C, and they're going to vary from 0.25 to 0.6, 0.1 to 0.4, 0.2 to 0.6. And I just picked those ranges because that's a non-simplex space. To be a simplex, the range of all the factors have to be the same, and then you might get a simplex. And here you can see the ranges are different. The range here is, what is it, 0.35, the range here is 0.3, and the range here is 0.4. Okay, and then the process factors you could put in, if they were temperature, pressure, or some other process factor, you could put in the levels. We're just going to leave them plus and minus 1. Okay, then we'd go to, after we've defined the mixture components, the process factors, we'd go to set it up. In version 12 of the software and setting it up, you can actually choose KCV model. So we just choose, say, KCV model, then it'll give us the terms that cross the linear terms for the mixture with the linear terms for the process. And then you can see here, AB, AC, AD, it's adding in the quadratic terms for the mixture without crossing them with the process. And down here where you see DE, D squared, E squared, those are the second order terms for the process without crossing them with the mixture. Okay, then we'd have the students run a simulation, analyze it, and we asked them to find process factor settings that maximize the response R1. Okay, so this is a type of design you get. Okay, so this design has, maybe I should have shown it on here. It doesn't show it. It would have the number of coefficients that are equal to, the number of runs that are equal to the number of coefficients in the model, plus 5 runs for lack of fit, plus 5 replicates. That should give you a pretty good design. And that gives you 25 runs, 15 for the coefficients, and then 5 for the lack of fit and 5 replicates. Okay, and then they simulate the response. We analyze it. Okay, now analyzing is something I don't really want to dig into very deep, but basically evaluate all the crossed models. So we're evaluating the mixture with just using the mean for the mixture, and then trying to fit the data with just the linear two-factor interaction, quadratic and cubic model for the process, then crossing those choices with the linear mixture, then crossing those choices with the quadratic mixture, and so on. We're looking for models that the model significant that for the mixture, and the model significant for the process, and the lack of fit would be insignificant. We'd have a high adjusted R squared and a high predicted R squared. Now the KCV models don't fall into that crossing pattern we're testing. So then what we do is we perform a similar test for the KCV model. And you can see there that the model p-value is very good. Lack of fit's insignificant. The adjusted R squared is higher by 1.3 units. so it's quite a bit higher. The predicted R-squared is lower, but you can see the predicted R-squared isn't real good here. And that generally, a big difference between adjusted and predicted just means the model has too many coefficients or it's over parameterized. So we'll see what happens when we reduce it. We should see that predicted R-squared come up. And so here you can see we're recommending the design model. And again, down here, it's saying the design model is recommended over the suggested models from the summary table. If this we thought was better, you wouldn't see these recommendations here. Okay, so we start with the KCV model. Okay, and there's the 15 coefficients. We're going to go in and reduce it, and there's a number of different ways you can reduce it. I happen to like the AICC, and I always like to do backward because it gives every model term a chance to be evaluated. So since I'm presenting, we'll do what I like. Okay, when we do that, we can see that the model reduces. Now we're down to 9 model terms out of the 15. And the model terms look pretty significant. The lack of fit is insignificant. The adjusted R-squared actually went up a little bit, but the predicted R-squared went up a lot. Okay, so now they're in good agreement. We have adequate precision. A ratio of greater than 4 is considered good, so 21 is really good. So that looks good. And now you'd look at the diagnostics the way you always would. The residuals, the externally studentized residuals should be normally distributed. Shouldn't see anything outside the red bands, should be kind of evenly distributed inside. Doesn't look like a transformation would reduce the error at all. The very best we could do in reducing the error is the green line. The blue line is no transform, and that's well within the interval around the green line. So going from the blue to the green won't improve it any. None of the points look like they're exceeding or coming too close to the limit on Cook's distance. So diagnostics are just looked at the way you'd always look at them. In this case, they look good. We can then go in, remember our goal was to maximize R. We can go in and run the numerical optimization and find the levels that maximize R. So it looks like a high level of A and a low level of B and a kind of intermediate level of C, along with the high level of D and the low level of E. Are going to give us the highest response. We could look at that on a mixture plot. Again, you can see we've got the maximum amount of A and the maximum, the minimum amount of B, and kind of an intermediate level of C. And we've got the high D with the low E for the value for the process factors. Okay, so once we've set up the design, the analysis is straightforward as if it's any other DOE. Okay, so if we look at this 3 mixture with 2 process, if I did the additive model, it would have 11 coefficients, but we'd have no linkage between the mixture and the process factors. Doing the KCV increased the number of coefficients by only 4, but we built in linkage between the mixture and the process factors. If we had gone to a fully cross model, it would have required fitting 36 coefficients, so over twice as many as the KCV. If there was really complicated dependence, we could have modeled that better. But it would have come at a cost in a high number of experiments. So if we had crossed the 2 models and eliminated the terms that were higher than 3rd order, we could have reduced that 36 to 27. That's still 12 more than what we had with the KCV. So you can see the KCV is always going to be much closer to what additive is. We get good linkages. And I said, we're using the ratios for many years, lots of published problems, lots of work that I did personally, found that those models fit pretty well. If they don't, and you need the cross model, you could always go back and augment your design with additional runs so you could fit those higher order terms if it was desired. Okay, let's finish up by looking at an exercise, and we're going to look at a company that was making corn dogs. Okay. And so ingredients in the corn dog is, of course, the hot dog in the middle. We're not going to study that. We're just studying the batter around that. And it's made up of flour, cornmeal, sugar, buttermilk. Those are the components that we're going to vary. Those are the ranges we're going to vary them over. Then we're going to add a constant amount of baking powder, salt, 1 egg, and baking soda. Okay, so these are fixed. These aren't going to vary. So we've got a 4-component mixture. And then we're going to look at 3 process factors. So these corn dogs are deep fried. They're frozen. You take them home. You put them in your oven. Okay, so we're going to look at the deep frying. And then we're going to look at putting them in the oven and cooking them. Okay, if we look at our model choices, we're going to be looking at, we think quadratic behavior in both would be adequate to model them. If we do a crossed model with 4 mixture and 3 process, we'd have to fit 100 coefficients. Okay, 5 for lack of fit. 5 replicates at a minimum, that's going to be 110. That's a lot of corn dogs to make and eat. Quadratic by quadratic, eliminating the terms higher than 3rd order, then well, that helps. It gets us down to 30 to 64. You say, well, the mixture part is going to have the biggest effect on the quality of the batter. Baking, I think, is not going to be as complicated. I could go with a quadratic for the mixture and 2 Fi for the process. I could cross those. That gets me down to 70. And say, well, that's still more than what I can afford to do. I could go with a quadratic and say, well, I'll just go with linear. I think that's a little risky when you're looking at time and temperature in the oven. They are going to interact. But if you did that and crossed it, you're still at 40. And now you've only got the linear by linear lengths that you have in the KCV. Then you can go the quadratic by the quadratic and use the KCV where we cross the linear terms and then we add in the 2nd order terms for the mixture and add in the 2nd order terms for the process. And we get a model of 28 coefficients. That is, quite a bit fewer than any of the other choices. And it's not that many more than if we just did an additive model, okay? Because again, having done DOE for over 40 years now, I've seen too often where the models get too big. So then the people say, well, we're just going to do the mixture and we're going to do the process separately. That's the same as doing the additive because it's all we can afford to do. Well, the KCV gives us an option that's not that much more costly and does a pretty good job of linking the 2 together. Okay, so again, I pulled this out of our course for the food industry. And so it's an exercise they'd be going through. So they'd be building this design with the 4 mixture components, the 3 process factors. We're going to put in the mixture components. They're going to add up to a constant in weight. Okay. We're going to have the 3 process factors and their levels. We're then going to design for the KCV model. Okay, and that's all handled automatically. We're going to use eye optimality. We're going to use the number of coefficients that are in the model selected, and then add to that 5 for lack of fit, and add to that 5 replicates. We're going to have 2 responses, the taste and the texture. And we're going to end up, they're going to build a design, run the simulation, analyze it. We're going to use the AICC with backward selection. We want to maximize taste and we want to maximize texture. Now, what we're going to do is we're going to use taste panels. We're going to have some of our competitors' corn dogs that we're trying to get corn dogs better than theirs, their frozen corn dogs. And so when they compare them, they're going to rate our corn dogs as 1 worse, 2 somewhat worse, 3 the same as the competition, 4 somewhat better, and 5 better. Okay, and so we're going to put a lower limit on both taste and texture of 3, which is we don't want to be worse than the competition, so we want to have at least 3, and we'd like to get as high as we can, and the highest we could get was 5. Okay, so we analyze this, and you can see we reduce the model. Once we do that, the model's significant. Lack of fit's insignificant. I've got a high adjusted R-squared and a high predicted R-squared, and they're in good agreement. I have a high adequate precision. So even with this KCV model with the linear by linear linkages, it's doing a really good job of modeling the behavior and the dependence of the mixture on the process and vice versa. Okay, so that was taste, texture. A little different model, but again, the model's highly significant. Lack of fit's not significant. Texture looks like it's a little harder to model. Adjusted R-squared is still good, 0.79, 0.68, so they're in good agreement, and I have adequate precision. Again, I'd look at the diagnostics and do all of that, but that's not the purpose of this webinar. So we'll jump right to the numerical optimization. And I'm trying to optimize both taste and texture. I'm giving them the same weight. The 1.7 and the 4.31 are the lowest tasting and the highest tasting individual result I observed in the DOE. And the same with the texture, the 2.08 and the 4.42. Now it turns out that it looks like I can interpolate between the runs I made and find a composition and a setting for the process factors that's going to give me better than what I've observed. You can see the blue dots a little above what I observed. So that's good. And you know, I'm going to be better than the competition. You know, I'm not a 5, but remember 3 was the same. You can see on the scale of 3 to 5, I'm past the middle by quite a bit. So that's good. So to summarize, if I look at the corn dog, if I'd done the additive model, that model has 20 coefficients and there's no linkage. Remember, that would be the same as if I did the 2 separate models as well. The KCV model has 28 coefficients and provides linkage between mixture and process factors. And at least in this problem, and I said many other problems I've seen, those linkages appear to be adequate, so we get models that fit quite well. And they don't always fit. In some cases, you'd have to go back and augment those. Sometimes you design for a quadratic and it doesn't fit. You have to go back and augment it to fit a cubic. So, you know, you've got the same issue here is you might need a higher order model or more linkages. And you can always go back and augment the design and build those in. Now the quadratic model with 100 coefficients and the cross quadratic model, leaving out terms higher than 3rd order, those runs were too large for them to do. They had a limited amount of time they could do these runs and limited resources to achieve it. And you know, the 38 runs, the 28 with the 10 extra ones was doable. 110 or 74 were not doable. Okay, so that's the end of the webinar on the KCVs. I hope you'll take a hard look at these and considering using them if you have opportunity to do combined mixture process work. Here's a few things. We have a blog posted that Geoff Vining wrote on the background on KCV models. So he goes into a little bit of the history of developing the models. And remember, Geoff was Scott Kowalski's advisor. Scott did this work as part of his thesis. And so he talks about that and their collaboration with John Cornell. So you can go to our blog. So when you download a copy of the slides from our website, just copy and paste this address into your browser. It'll take you right to that article. The next webinar we're going to do is in May, and it's going to be on simultaneous optimization of multiple responses. If you want to learn more about Features in Design Expert, this webinar and lots of previous webinars are recorded. So we're recording this webinar right now, and you can go to our website and look at those. To give you an idea of some of them that are available, I put my favorite topics on there. Turns out that I'm biased, so my favorite topics are generally webinars I did, and they're not my favorite topics because of the webinars. They're my favorite topics because I only do webinars on things that are my favorite. So it is a little bit biased. You can go to the website and see all the webinars. You can also attend a public workshop. We have workshops on mixture design that would include what's in this webinar, or we have a number of other workshops you can see on our website, or you can bring us on site for a private training course. Okay, here's my list of webinars: sizing for precision, both response surface designs and mixture designs. I think it's really important to size them to get the precision you want. It's another tool you have to judge whether or not the design you're going to run is going to be adequate for your purposes. It's a lot like power in factorial designs, but power doesn't work well for RSM and doesn't work at all for mixtures. So sizing for precision is a tool that works. There's actually 2 webinars we've done. So I listed them both, the size mixture, RSM designs for adequate precision, and unleashing evaluation. So this includes sizing for precision along with some other tools used to evaluate design. So there's a couple of webinars there. The webinars that I listed in blue are what we consider intermediate. The webinars that I listed in red are what we considered advanced. The webinar I just did is an intermediate webinar. Dealing with multilinear constraints and nonlinear constraints. We have a webinar on that. Propagation of error, we have a webinar on that. Practical tricks of the trade, so that includes using CPK and PPK for optimizing, along with a lot of other useful tricks, I guess I'd think of. And then finally, using intervals to frame your operating space. So if you want to frame a space where you can meet specifications with high assurance, this is a good webinar. For those of you in regulated industries, this relates to quality by design that they use in pharmaceutical and medical devices. So that's the end of my webinar. I want to thank you for attending, and I hope you've gotten some value out of it.